Okay. This is looking really dim to me. All right, so let's get started. Sorry about the bad projector, but that's how it goes. So today we'll talk about sort of the lifetime of a program, not a process. That'll be later, but going from sources through compiling, through preprocessor, through compilation, through linking, and then maybe to the loader, and we'll take a little bit of a look at the assembly and so on, see what's happening in there. But before that, perhaps if there are any questions on homework 3, garbage collection. Who's committed something? Oh, that's a good start. Did you commit the template? Okay, who's committed the template? Okay, I propose that you always start by committing the template, because it's not like you're going to lose any grades, any points by submitting a template, or even a bad solution rather than no solution, right? And it gives you the advantage that now, you already committed something bad, you might as well commit something new that's a little bit better, still bad, right? So now you have a version history of things that kind of work, and then toward the end, rather than making 100 different backup copies on your machine, toward the end, when it turns out your last solution doesn't work, now you can always back up to the previous one at least, and that'll be okay. Or you could maybe you could even convince Tim that, this previous revision, can you just grade the previous revision instead? Maybe. You won't get a full grade for it, but.
Can you pull all the revisions from SVN, or?
Yes. Okay. So if you want a different revision, you SVN up and you say -R, or if you want to check out the new one, you say check out the same as always, but then -R for revision, and which revision you want. If you want to see what revisions there are, you would say SVN log in your repository directory, and it just says everything together with those messages that you're supposed to write, which can be handy. Great. No wireless either. Well, maybe we don't need the wireless today. Let's see. All right. Well, when I need the connectivity, I'll go check for it. Okay, so the topic of today then, the whole going from a binary, so from source to binary, basically. So let's first maybe overview what's happening. So I think it's a very good idea to know really what's happening in your little piece of C program. You sort of have an idea of what does this include do, right? It seems to not quite finish the job. You sort of get some pieces that you need, so you can compile part way, but then it gets upset anyway with some weird .o messages or something. Right? So is this something that Thais talked about last? So you're saying Thais talked a little bit about linker errors and that sort of thing?
Well, not much, just about the basis of what compilation is.
Oh, okay. So maybe we'll just quickly refresh then. So we've got from sources to binary, and the chapter to read, or section to read, is number 7. And I'll put up the specifics. There's some sections that we can skip, little subsection we can skip. I'll put that up on the website. So here we've got first a preprocessor step. Get rid of all the hash marks. Okay, so you got all these includes and stuff. There's nothing left after the preprocessor is done of all those hash things. Instead, your program just grew a whole lot larger. We'll see that. And then you have a compilation step, compiling, and that takes .c files to .s files. Okay, anyone surprised by that part? No? Okay. So the S files are assembly files, right? Now we assemble the .s into a .o, and that is a binary object. But now those binary objects, there's one binary object for every C file. So if you have lots of different C files, you don't have a program yet. In fact, you can't even run a binary object, even if it's just a one C file. Now you have to link it to make an executable, and almost always you'll be linking with libc and with crt.1, and there's some basic things that just help a program get started in the Linux environment. So linking takes multiple .o files and the .a libraries and .so libraries to an executable. Very good. So the libraries in general are collections of .o files. So you can think of it as just a directory, but it's been put in a particular format, so it looks like one file. .a library is exactly that. It's you can decompress it with the AR tool, and it'll unpack into a bunch of .o files. It's a static library. .a files are static libraries, so if you link with a .a file, your program will grow by the size of that .a file, but not quite. If you only use some of the .o's inside of the .a, right? So I'm using, say, printf out of libc. I'm not using all of libc. It'll grow only by the size of the printf.o file inside of that archive. You could also imagine having a libc.o file, but that would be a very large file, and then you would grow your own executable by that size, even if you never use, say, scanf. Scanf is probably a big function, but we never use it. It's better to have a small binary. Okay, .sos are completely different. Those are the ones that are shared. They're shared object. That's what SO stands for. They're shared libraries, dynamically loadable shared libraries, the equivalent of DLLs in Windows. What happens there is the whole thing actually gets mapped into memory. So it's not necessarily sitting in memory. Your own program doesn't grow by almost anything. It grows by a tiny little bit. There's some indirection going on there. And then when you start the program, you see, oh, is this already mapped into memory? If so, you get that part. If not, you map it into memory. And then you start accessing just the functions that you need from there. So that actually has the full size of the library. You always have to ship your program with the .so if it's not available on the machine. So in that sense, it grows larger, but it doesn't use very much memory because it's memory mapped. So you're only going to get those pages that you really need from that. Another nice and dangerous part of the shared libraries is that you can change the shared library on your machine. So you wrote a program, you compiled it, everything's fine, you think you're done, and now so you run it and everything works. And then you go and update your libraries, and suddenly your program doesn't work anymore. Right? So, because your program is going to be loading these shared libraries every time it loads the new version of the shared libraries, and it might be a problem. So there's some version management going on in Linux, but we can skip that for now. In general, that's difficult, whereas the static linking, then you're always using the same version, which means you have to update every program instead. So it's a trade-off there. If there's a bug in the library, you have to update every program that uses that library. Okay, so finally we have the executable, and then of course there's the loading phase, where we are more or less mapping the executable and any .sos into memory, and then well, we haven't really gone into this yet, but you're sort of taking over an existing process. Okay, so we'll see this later, but there isn't actually a way to just start a new process. And it might exist in Windows. I'm not familiar with the internals there. But in Linux and Unixes in general, only one process is ever started, and that's the init process. Maybe you've seen this. So we'll take a look at that while we're at it. So here, if I run top, maybe I can see the init somewhere. No, I can't. Was it there? Oh, got lucky. Great. So you see here, process ID number 1. That one actually got started by the operating system. None of the other processes got started. What happened was, init got copied, and then one of the copies decided to replace replace its code with some other program. So that's what happens every time. The replacing function there is called exec, but that doesn't actually start a process. You get killed, and you start running someone else's code. So the only way to make a new process is to fork yourself, make another copy of yourself, and then realize that, oh yeah, I'm the copy. Let me commit suicide here and replace myself with some other code. Then of course it keeps going like that. It's not like init keeps forking all over all the time. It's all sorts of programs can fork, including this program here that we're using, right? The shell. We might end up writing our own little shell for a homework later on. Okay, so getting back to this then, let's take a look at all the various phases in a little bit more concrete. So I'll make a bigger window. This is really a bad projector. Okay, so what do we call this? Hello world.c. Actually, I should be nice here. I'll do the whole thing. So actually, it doesn't matter if I write out this whole profile. If I'm not returning anything, and I'm not actually using these arguments, it doesn't matter. The function call is the same anyway. They're going to put the calling function. We probably talked about this in 261. The calling function puts some stuff on the stack, and then jumps to me. Right. So. And then I have the base address is on their previous base pointer is on the stack and so on. Right, so I know how to return without actually agreeing on what the profile of this function is. Right, I can make this take whatever as long as well, yeah, they call me and it's fine. But of course I won't be able to use my arguments if they're not the right ones because they put some stuff on the stack and there's no way to verify that they actually put that on the stack. So there sort of has to be an implicit agreement on what to put there. So that's what we use the include files for, really. So let's put one of those. And then I'll print something. Okay. So, oh, that's a little too many. Yeah, thank you. Okay, so you may have noticed that you can actually run this without this include here. So, well, let's try with the include first and just see what's happening. I'll make another window. Okay, so now we want to, what was the first step? Right? We want to run the preprocessor. Of course, GCC does all of these things for you behind the scenes, but we want to know what's really happening in case we want to change it at some point, or in case we want to, futz around with binaries or this sort of thing. That's what being a computer scientist is all about, right? Actually knowing what the computer is doing, not just how to make it do something. So, okay, we have a program. We want to just run the preprocessor. Goes like this. All right. So actually, we need a bigger window, don't we? So what happened here? There's my hello world. Right. That's the program. So this include here, all it did was tack on some other stuff. Let's see, how much was it? Okay, so we're now up at 850 lines. That's all that this include thing does. And what's in there, you find there's no actual code. There's just all these little declarations saying, oh yeah, there exists a file somewhere else sorry, there exists a function somewhere else that has the name scanf, fscanf, and it looks like this. Okay, so that's helpful, because if I go without this, I have the same program. Okay, so there's nothing there now. If I want to assemble it, that's still, or compile it, that's still going to work. Let's see, we go, how is it? Oh no, it's S. Let's see, did we get one? Yeah. Okay. So that's our main, and that works fine. And now we're calling. Oh. Yeah, this is unfortunate. Let's see, GCC does some funny business with printf because it's used so much. They have some built-in printf function that they keep replacing. So you see this actually, it translated this. I didn't want it, but it translated my printf to a putS because that's much faster if you just want to print out a constant string. So we want to get rid of that. Let's do that. I have to find out what it's called.
You can probably make it just printf quote %s quote and then toss hello world there.
Yeah, but I wanted to actually do this right here. So there's a way to, it's like no built-in or something. Let's see. No, no built-in dash printf. Oh, maybe just no built-in in general. Flicker, flicker. Okay. See what it does then. Hey. Oh, so why is it not even complaining? It's weird. Anyway, let me sure I get something right here. Okay, good. Okay, so we want S. No, F is for flags. So I don't know why it didn't complain when I passed this other thing in. But anyway, so the C, we don't need that.
Single dash.
Single dash. All right, there we are. Let's see what comes out. Oh, there we are. Okay, so we say call printf, but we don't have a printf. All right, so the compiler doesn't really care, it seems. Maybe it doesn't even complain actually. You could probably get a warning if you tell it, oh, warn all something. You could say, oh, this is an undefined function. Do you really want to do that? It doesn't seem like such a good idea, you know. But it's not really going to be a big problem because we still have the name in here. Right? We have the name that says, okay, we want to link with a symbol. Where's my pointer? Oh yeah. We have a symbol called printf. It's going to show up at some point. Right, so we're just going to have to, later on, we're going to find another .o file that we're going to put it together with to somehow make this binary. Because the printf was never in here anyway. So let's try it one more time. But now I'm going to do it with my standard I.O. So here's the assembly, right? Now check it out. We run it one more time. I don't think it changed. So the compiler doesn't care. It cares in the sense that it can be helpful. Right? It can say, oh, you're trying to pass some parameters here that doesn't really look right. Yeah. But it's not actually going to get in your way. Okay, so the problem happens later on because you can't make a binary that has a call to printf, but we have no function printf. Binaries, the only thing that binaries can call on their own are system calls. There's about 200 system calls, and I promise you, none of them is called printf. There's well, we'll ignore the list of system calls now, but it's a very restricted set there. Write is the one that printf uses. So way in the bottom, it has a file handle and is writing a few bytes to this file handle. Okay, so that's fine. Now we have a compiled assembly in our .s. I think I heard someone say, what's less? Less is just if you've ever used more, it does the same thing, but it's not as good. So less is more.
Which one's not as good, less or more?
More is not as good. So more, I think it's called more because if you hit space, you get more of the file. But then someone was figured, oh, we can make a better one. So here you can search and things. Right. So less is like more, but better. Okay. So next step then, we have our assembly file, and now we want to, of course, make that an object file. So what do? We'll take our assembler, AS. Oh. We'll have to tell it where we want it, and then which file are we assembling. Okay, so now we are in good shape. Oh. Let's see how big this thing is. Not bad. Okay, a kilobyte. All right, so this is still a fairly complicated program, and I think it's maybe a kilobyte because it's hard with all the headers and stuff. You can't really make a smaller object than that. I'm not sure. So we'll take a look at what's actually going on in here. So now this object file, now it starts being a little difficult because if you say less like this, I mean, that's not very helpful. So how can we know what's going on inside of our object files? Clearly, we saw the assembly. Actually, maybe we can go back and look at the assembly one more time because there was something I forgot to show you. You remember how the S, let's see, where is it? Oh, we never made a file out of that. Did we? Yeah. Here. This is a huge file, right? And now when we go from that to assembly, actually we can take that into a separate file just to show you that everything's really happening the way I'm saying. Call it like preprocessed C, like that maybe. So there's our preprocessed C, and now we want to compile that into assembly. Oh, nice. Okay, go like that then. What? There. All right. So now we have our less 2.s. Oh, it's capital S. There. Okay. So now those 800 lines turn into this. All right. So all of that other stuff, all those extern blah blah blah, there's no actual code coming out of it, and it's gone now. We're not going to be looking at that anymore. There's no step along the rest of the way that cares about all that stuff from the includes. So those includes were mostly there to help us write a better program. Yeah.
Why did the .NET promise so much empty space between functions?
In the .s? Oh, the pre-processor one. Yeah. I have no idea. I mean, so actually I have an idea. Standard IO.h. Let's see what it looks like. Include IO.h. So all these comments are not going to make it in there. Get rid of those. So there's comments all over the place. That's part of it. And then see here, you got another include here. It's not like, oh, all of that stuff is in here. There's just some of it in here. The rest is more includes that are then recursively included. And so now you have an include, and inside of that file there's some more comments, and they also get stripped out. So, and between the comments there's white space, and maybe it doesn't feel like removing white space. But it's not important, clearly. Okay, so let's get back to this here. So what do we have? We have our main function in assembly. Everyone's familiar, kind of familiar with the assembly, I presume. So our main function, it doesn't do much, right? Well, what else do we have? This is some metadata. Says something about who made it, looks like. And then the string is sitting in a separate section. In the read-only data section, right? And then we have our text section. I can't see. Oh, there it starts. Here starts the text section of the code, and they end up in different memory mapped regions. I think we looked at that before, right? In the proc map thing, it shows 3 entries for every binary. One of those entries is this part here, the read-only data. Another part is the text, and another one is any global variables. Okay, anyway, so that's all there is to it. And after this, we have to forget all about our source code. Right? So now the next step was to assemble this. We did that like this with the assembler, and of course GCC does that for us too. And now we have our binary. So let's see what's in our binary. We can use readelf. It's a very handy little tool to get an output of all the sort of metadata in that in the object file. We're not looking at the assembly here. We're just saying, oh, like, what does this thing contain? Let's see. So what do we have? It starts off saying, okay, it's an ELF32 file, right? So ELF is just one of those binary formats. It's not an executable, but it's still, you need to have a binary format so that the linker knows how to read it. Bunch of stuff. Oh, what kind of architecture are we running on, and so on. Then comes some interesting pieces here. All the different segments in this file. Most of them are not going to be very interesting, but here's the text segment. What do we have? 32 bytes into it. We have a text segment of 18 bytes. So that was our assembly. Do we have it? Let's see. Does that fit about 18 bytes? Yeah, it looks like this is nothing. This stuff is debugging. Actually, it's not quite debugging. It's stack frame format for C++, so it can handle exceptions correctly. It doesn't end up actually being assembly here. It goes in a different section. We can ignore all of these CFI things. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sounds like about 18 bytes. And then we had some space for this. What is this? That's probably about 10, 11, 12. It looked like, if we go back here, what do we have? It says 18. 18 in hex. So it's 24. Okay, so 12 bytes for our text, probably, or... Oh, no. What's using up the first few? The first 24 bytes must be this then. So the ELF header is probably 24 bytes long. That's the just where. Oh yeah, there should be an init here too. Where do we? No, this is not executable. Sorry. Okay. So those are all the sections, all the things we need to worry about. Probably text is the most important one. That's the program. Okay, let's go down a little further. What do we have in here? Well, we have symbol. This is a function that we're declared. So we're saying, oh, in this object, there is a symbol called main, and it starts, it's size 24, and it starts at, doesn't say where it starts at, where is it? A little further down, maybe? Huh. Why does it not say where it starts? We probably need to have some other flag to output something more. Okay, there's one more piece here. It says, okay, we have a reference to printf. Right? So we're saying, oh, there's a relocation entry here saying this object file requires printf, but we have no printf. We do have a main, and then there's an undefined here, undefined printf symbol that we're kind of going to use at some point. Okay, but actually this is probably what we should treat as requirements. So we need, since this is undefined, we need a printf. So when we're linking later on, we'll be looking for printf. But then once we find our printf, how do we, the program just says call printf. Actually, what does the assembly look like? We know what the assembly looks like. What does the binary look like? We can't call anything. right? Because we don't know where printf is. If you call something, you call to an address. You don't call in assembly. You don't call to a, or sorry, in binary, you don't call to a name of a function. How would that work? It's got to be call to this destination address. We don't have the address. So what are we going to have there? Any thoughts? If we disassemble our main function, it says call, of course, but what is it calling? Can't call anything. Let's take a look at it with object dump. They're both the same, right? So I'll take this one. So we got what? We got a call, and then to main plus 12. So it's calling to the byte right after this. It's nonsense. Doesn't mean anything. Okay, so we have a piece of nonsense code in here. Now how are we going to make it call the right place? Right? So now later on we have our own printf function that we want to call in another .o file. Now we know where it's going to be. We tack those together. We kind of just take the first .o file, the next .o file, the next one, just one after another, append them all into one large file, and then we're going to have to change all of this code. Right? And it's not like we're changing the text. We have to change this part here. Right? That has to call somewhere else. So this is... Why does this mean main plus 12? That I don't know.
Well,
but
you shouldn't read the whole thing as just being numbers. Encoded instruction to begin with.
no, this is the call, I think.
Yeah.
Just the E8, probably. It could be both of them, but...
Because isn't main just 0, 0, 0, and then it would turn out into a negative?
Yeah, but it should be plus 12. So I'm a little confused by that. Maybe it's just how the disassembler decides to represent it. Like, oh, here's a nonsense thing. We always go with plus 1. Okay, so anyway. So now we have to fix it. How can we fix it? Right? How can you run through this program here and find the places where there's a call to what should be printf and replace it with something else? Right? This does not look like printf to me. And this part here certainly doesn't look like printf either. We don't have the assembly anymore. All we have is this object file. You can't do it. There's no way to tell that this was a call to printf. So what we have to do is some extra data. It's called relocation entries. We need to remember all the places where we meant to call printf. Where were they? Right? And then we go back with the linker. The linker will replace every one of those entries in our object file with the right value, the right address for printf for our current compilation. So if we make a larger program, it's going to be a different address because now you have a bigger thing on top. When you're putting everything together, all the offsets are different and so on. Okay, so those are the relocation entries over here. Here's a relocation entry, and it says at offset 12, right? We need to insert, it's a 32-bit entry of some sort. I don't know what this info is. So, but anyway, so it says, okay, printf. Whenever you find printf, run through this object file, replace all these entries, this is only a single one in this case, replace all of them with the address of printf. Okay, so that's what the linker does. Let's see if we can do that. So now we want to ld homework.o. Can we go like this? See, maybe if I put it, if I include the lib i36, I think I know where this underscore start sits. It's in this crt1.o. Ah, damn it. Okay, so that wants some more. So, see, it said here, okay, we have a we have a call to printf, that's fine, but there was apparently a call to start as well. I don't know where that's, oh, that's, there's always got to be a start. In every program there's got to be a start. You think there's got to have to be a main, but that's actually not true. For LD to make an executable, it requires there to be an underscore start function in one of these objects. If you can't find one, it won't make an executable. Okay, so that start function is actually in this CRT1 on Linux. It happens to be in this CRT1.0. So now I found it. But unfortunately, if we look at the CRT1.0, we were close, right? But it didn't quite work. We want to read elf. I will probably find some more undefined here. Where's our symbol table? Oh yeah, here we go. Undefined this, undefined that, undefined main. Okay, but we haven't had a main, right? So that's good. So we got past that. But now we have to find the libraries that hold these functions too. And let's not go there. Okay, so I don't remember where those are. And I'm not going to be searching for it because there's hundreds and hundreds of these files. So we'll just ask GCC for a little bit of help in the last step this time around. Maybe I'll post it on Piazza which files it actually was. So we'll say GCC, please compile, what was it, homework.s. Thank you. Let's put it in. Alright, so that makes an a.out by default, which is a strange name for it, especially given that the file format is no longer a.out, but that's an aside. So let's take a look at our a.out then. Okay, so what do we have in here? Where's the stop? Here, okay, so the start entry point address is this. Okay, so this is where the program starts running. Let's see if we can find that in here. So if I do with a less, we'll be better off. See if we can find this. That should be in our symbol table, hopefully. Oh. Drat. Okay, 8048330. So it's going to be inside the text. Can't see the text. Oh, there. Oh, it's at the very beginning of text. That was nice of it. But probably we'll have a symbol for it as well. Or maybe we don't. I don't know. I don't know why not. No, for some reason we got a Gmon start, but we don't have a proper start. That's a, oh, those are the dynamic symbols. Let's see, maybe it's more here. Okay, a lot of good stuff. Some of the, there it is. So why didn't I find that? What was I searching for? 0x. All right, so if I search just like this, then we're good. Okay, so there it is. The first start function, we can go look at that too. You'll find that that actually calls some other libc start blah, and then eventually comes in and calls main, right? And that's where we start working. Okay, let's see. I think there was something more that was interesting over here. Actually, we don't have to look at anything. We don't have to start searching for anything. We can just look at our entire binary. There it is. Start. Okay, so here's start. So why does this work now? See, I'm disassembling my binary, and now suddenly I have these nice annotations here. It used to say, oh, main plus 12, that sort of thing, and now I have nice annotations saying exactly what I'm calling. Any ideas?
Is it something to do with page tables?
Nothing to do with page tables. No. Got something to do with another table. In our, oh, this is the wrong one, but in here we have a large symbol table that says, oh, what are all the functions in this program? Right. Those are not required, but by default the symbol table comes with the binary. You can strip them. That makes the binary shorter, but much harder to work with. So now when I'm disassembling, the disassembler runs into a call and then an address. Of course, he'll just look it up in the symbol table and say, oh yeah, it's that one. All right. Can't do that before you've actually linked in with the right stuff. Okay, back to this. Let's just follow it down, see what's going on. So we call libc start. Okay, and that then calls underscore init. See if we can find that. Oh, that's CSU init. That's a different one. That was probably at the top. There it is, init. What does init do? Calls. Oh. So this is not init. This is not a call. Huh? It says, oh, if EAX equals to EAX, whatever that's supposed to mean. Oh, it's not an if. It's a. What does this test do? Anyone know? It's an and?
Yeah.
What good is that?
It sets off flag.
It says if it's equal to 0.
Yeah. It sets the flag for the jump.
Oh, so it sees if EX is 0. Okay, that makes sense. Ah, yeah. Okay. So anyway, so we're jumping forward to init plus 1f. Where's that? 2d3 here if it's 0. Yeah. Okay. I don't know which one is which. Probably it's going to be this one. Right? So if we're gmon, I don't know what that is. Might have to do with the profiling, but I'm not sure. So frame dummy, let's see what that is. Might as well. Oh, actually, we have gmon start right there. Like, you can see what it does. Huh. Seems like it's putting some crap on the stack. Okay, it's good to know.
Yeah, it's gprof related.
Okay. And then what? Call whatever's in EAX. Okay, that one's a little harder to follow.
It's 8049F24.
Really? But it's.
Unless.
What about this one here? So it's jumping. Oh, if it's 0, then we jump somewhere else. But if it's not 0, then we're going. Then we're going through it. Oh, okay. So it's probably. Wait. E1. 3E1. Oh, it goes to here. Oh, so it goes back. So that's not the one that makes the call. Good. Okay. So we were close. Where was it? This was an init, right? Do global CTORs. Constructors. Maybe. That's not it either. Shall we see who's calling 1 here instead? See where it actually happens. That's hilarious. Okay, so the actual code that calls main isn't in our binary because I didn't link this static. I linked it dynamic. So part of this is going, and we don't have probably enough time to go into dynamic linking today. We'll do it next time. But part of this program is in this dynamically linked library, right? And that's never going to be in my file, my executable. It's sitting in memory somewhere, and it's going to be pulled in when we start running. That's a whole different game there. But let's see. Maybe we can at least see that. So relocation entry, there should be a PLT here somewhere. Ah, here. So there's some relocation entries called PLT, procedure lookup table. So these are things that the libc start main, it doesn't actually exist in our program here. That's something that's sitting out in a dynamic loadable library, and so we can't get to it right now. When the program starts, it gets run with LDD, it's called. That will pull in these functions and then do the replacements. The offset here. No, it's somewhere else. But anyway, it'll do these things on the fly, right? So it'll figure out what the offsets of the printf is, and so on the fly. Hold on, don't run off yet. We gotta do this static. Here. Now we ought to be able to see a little more. Oh yeah, so object dump. Now we should have printf in here. I wanted to find printf. There's libc start main. Okay.
What are we looking at right now?
Just search for less than.
I want to show you all this. Oh, you think we should search for that?
Probably underscore.
Yeah. I do not. Anyway, we can certainly find our main now. Whatever calls main, because there can't be another place for something that's calling, so let's go find it. Hopefully not that many more of these suckers. Do main, do main, do. Awesome.
I mean, this is the dynamically linked.
No, this is statically linked. Okay, so what should we be searching for here exactly? We should maybe search for main like that? No. Damn it.
This is really good. It does not want to.
Yeah, where is it? Maybe if we find our main function. There's too many of those too. There. Okay. And then we can see what it's actually called in the code, maybe.
Then it
Oh, the
needs to be
CD0.
0. Okay. There it is.
Yeah, that's main. Yeah, but I wanted to find the call to this main. Yeah, so it certainly looks like it would be like that. But it's not. Okay. Bear with me. Let's try this one more time here. Oh, this is not the last time we're going to be doing this kind of code surfing. All right. Okay. Well, damn it. Okay. We're out of time. So I'll find that line. I'll post it on Piazza. All right. See you on Friday.